For centuries, people believed something very natural. If parents acquire certain characteristics, their children may inherit them. It sounds reasonable. A muscular father should produce muscular sons. A hard-working family should produce naturally hard-working children. Large plants should give permanently larger offsprings. But science has a dangerous habit. It often destroys ideas that feel intuitively obvious. Around the beginning of the 20th century, a Danish scientist named Wilhelm Johansen asked a question that sounds simple but is actually profound. Are observed characteristics truly inherited? And instead of arguing philosophically, he took help of statistics, and statistics came out with some hidden truth that made surprised and shocked the scientists of that time. The way of finding the fact was so elegant that the famous mathematician Mark Kirk later called it one of the finest demonstrations of statistical reasoning he had ever encountered. And I promise you, by the end of this lecture, you will never look at a histogram in the same way again. Let us travel mentally to the late 19th century. Darwin's theory of evolution had already shaken the intellectual world. Natural selection was now a serious scientific idea. But there was still a major problem. Scientists didn't yet properly understand heredity. How are characteristics transmitted from one generation to other generation? This uncertainty gave rise to intense debate. Even today, many people casually think in this manner. We instinctively confuse what is observed with what is inherited. And this is exactly where Johansen enters the story. He decided not to rely on intuition. He decided to let data speak. He decided to take the help of statistics. Now comes the beautiful part. Johansen collected a large number of beans, not hundreds, not a symbolic sample, but a sufficiently large population for a serious statistical analysis. Then he did something revolutionary for biology at that time. He measured carefully, systematically, patiently. Each bean was weighed. And then he transformed these measurements into a histogram. Today, this may look elementary to the students of statistics, but at that time, This way of thinking was intellectually transformative. Suddenly, biology was becoming quantitative. Now, what did the histogram show? A bell-shaped pattern. Most beans had medium weights. Only a few were extremely small. Only a few were extremely large. In modern language, the distribution looked approximately normal. At this point, Johansen performed the crucial step. He separated the large beans and the small beans into two groups. Then he planted them separately. Now think like a scientist. If size itself were strongly inherited in the naive sense, what should happen? The descendants of large beans should become permanently larger. The descendants of small beans should become permanently smaller. In a statistical language, the centers of the two future distributions should move apart. Simple, logical, reasonable. But statistics often surprises us. When Johansen examined the next generation, something extraordinary happened. The offspring distributions looked almost the same. The descendants of large beans didn't continue permanently larger. The descendants of small beans didn't continue becoming permanently smaller. Both distributions drifted back toward the original average. This was shocking, surprising. Because it meant that merely selecting extreme individuals does not necessarily create permanent hereditary change. Let that sink in. What you observe if an individual may not reflect what is truly inherited? Some variation is hereditary. Some variation is environmental. Some variation is simply a random fluctuation. And suddenly, a profound scientific distinction emerged. Observed characteristics are not automatically inherited characteristics. This might become foundation for modern biology. The mathematician Mark Keck later wrote beautifully about his reaction to Johansen's experiment. As a young student, Keck was deeply impressed not merely by the biological conclusion, but by the style of statistical reasoning itself. Why? Because Johansen was not arguing philosophically. He was relying on anecdotes. He was not saying, I have seen large beans produce large beans. Instead, he used measurement, distributions, average, comparison of population, statistical inference. This was entirely new mode of scientific thinking for many students at that time. In this way, statistics transformed vague biological speculation into quantitative reasoning. Thank you.